This is an example problem for using separation of variables to solve the following situation. We are asked to find the potential everywhere inside this what is called an infinite slot. We have these two planes at z equals 0 and z equals a, and so this distance here is a. On these two planes, the potential is set equal to 0. We're going to say that the potential dies off as you go into the positive y. As positive y goes to infinity, the potential dies off. And we have the condition that the potential is some finite non-zero value v naught at y equals 0. And so we can go ahead and write those conditions. Our differential equation is, of course, just the Laplace equation. And so that's going to be minus del squared v is equal to 0. The conditions that we're going to have, first off, is we're going to say it's independent of the x direction. So we're going to have v of this r vector is going to be simply v as a function of y and z. And our boundary conditions, as I said before, are that v at z equals 0 and v at z equals a are both equal to 0. And our boundary conditions in the y direction, so these are in the z direction. You'll notice that both of these are the boundary conditions in the z direction. And then our boundary conditions in the y direction are going to be, I guess, limit as y goes to positive infinity of v of r must be 0, and that v r at y equals 0 is some non-zero value. See, these are our y boundary conditions. Okay. So in order to proceed with a separation of variables, the usual trick that we have, right, is we're going to say that this v of two variables is equal to a, let's see, the way we usually write this is a product of functions of a single variable. So we'll do y, capital Y as a function of y, and capital Z as a function of lowercase z. And so that's our two functions. Through some manipulation, and the manipulation is always the same, the Laplace's equation. Okay, Laplace's equation is going to give the following two equations. In the y, we're going to find that the second derivative of capital Y is equal to cy, capital Y. And we're going to find that the second derivative with respect to z is equal to cz as a function times z as a function of z. Now, we know that the solutions to these two things are simply sines and cosines. So for both of these, okay, we're going to get either exponential of plus or minus the square root of cy or cz times x or y or z, right? Or we're going to get sine and cosine of the square root of minus cy cz times y or z. Okay, that's just what the solutions are going to look like. We've seen these type of differential equations many, many times before. We should just immediately recognize, depending on the sign of cy, if cy is positive, you get exponentials. If cy is negative, then you get sines and cosines, such that the square root here would be a positive number. Now we have to use a little bit of forethought and see if I have 0 here and 0 here, and I want a non-zero value somewhere in the middle, the only functions that work there are the sines and cosines. And so this is going to make a statement that in the z direction, I'm going to use this to justify that cz must be less than 0. Okay. Oh, there's another condition I didn't give you here. and that's that with these two things together, we have that cy must equal to negative cz, or the sum of them must be 0. Okay? So we've justified that cz must be 0 because if we have 0 here and 0 here and we want non-zero in the center, I cannot do that with exponentials. There's no way to add them together to do that. I can only use the sines and cosines to do that. So moving forward, now the goal is simply to apply these boundary conditions. Now we're going to work in the z direction first because that's simplest. And the first thing that we're going to do is we're going to let cz equal minus k squared, and we choose that because if cz is a negative number, then k can be positive or negative and cz will still be negative. In addition, we choose it because we're going to be taking the square root here, and our function is just easier if we don't have a square root hanging around. So rewriting our differential equation, d squared over dz squared, capital Z of z, is equal to minus k squared, capital Z of z. And this is going to give us as a solution that z of z must be some a sine of kz plus b cosine of kz. Now we want to apply the first boundary condition. Okay, the first boundary condition, let's go ahead and bring that up. Here's the boundary condition in the z. I'm going to use this one first, and that v of r at z equals 0 is going to be whatever the y function is. So this will be whatever y function is as a function of little y, and then times this evaluated at 0. And so sine of 0 is 0, so this is simply going to be b cosine of 0, but cosine of 0 is 1. And this is equal to 0. That's our boundary condition. The only possible solution that's valid for all y is that b itself is equal to 0 as a quantity. Now we're going to apply our other boundary condition here. So the second boundary condition is this guy. So that is v of r z equals a. Sorry. And again, we're just going to get whatever the y is. We don't have to explicitly write it out yet. And then here, b is already 0 from the top, so we're only going to have the a. So this is a sine of ka. This must be equal to 0. Well, this is only true for all y if either a is 0, but if a is 0, the whole thing's 0, and that's uninteresting. The interesting one is when this is going to imply that sine of ka must equal 0, and this in turn implies that ka must be an integer n times pi. And here we can be a little bit more specific. N can't be 0 because if n is 0, the sign of 0 is 0 everywhere, and that's an uninteresting answer. If n is negative, it's the same. It looks the same as if n is positive. I could just change my a to minus a and it wouldn't change anything. And so the only independent solutions here are going to be, this is for n equal to 1, 2, 3, dot, dot, dot. Now, I went through the analysis on how we justified that we only cared about n 1, 2, 3. Truth be told, when you're doing these problems, you do this again and again and again so many times that you just tend to memorize that when you have the signs, you only care about the positive integers greater than 0. Okay, so that you just learn this after doing this a few times. So now we're actually somewhere. So the result out of here, right, is that k is n pi over a with that condition. So that's kind of the result we have so far. Now let's look at the y condition. Okay, so first the y differential equation, we're going to let now cy would be equal to positive k squared, okay, which we now know is n pi over a quantity squared. So the differential equation is partial squared over partial y squared. Truly, I guess it is partials, but it doesn't matter at this point because we've changed functions of a single variable. Now we're going to have a positive number here, so this is n pi over a squared capital Y over y. And the solution here, right, is going to be that capital Y of y is, let's see, we used a, b, c was used there, so let's go to d, exponential of positive n pi over a y plus e exponential of minus n pi over a y. Now for the last condition, I'm going to immediately apply this condition before sticking stuff together, simply because I can here. And so that condition is the limit of v of r as y goes towards 0, infinity, positive infinity, must be 0. And so for us, that's going to be whatever the z of z is. Okay, it doesn't matter. Z of z. So I move that out front, and then the y part is going to be this. So this will be d e to the minus, to the plus n pi over a y, but this is going to go towards positive infinity, plus e, Euler e to the minus n pi over a y, but in the limit as y goes to infinity, this is going to go to 0. So this part's ignored. If we have a non-zero value for d, this is going to blow up as we go off to positive infinity for our problem. And so this is implying that capital D is also equal to 0 in this case. So I'm going to take these two results that we have so far, okay, and so I'm just going to summarize the two results because I'm not sure I've done that so far. We have that y is going to be equal to a sine of n pi over a, so this was z, I apologize. Okay, so we'll do this, but we're just going to do this here. Okay, we're going to start off z as a function of z is a sine of n pi over a z, and we have so far that y, capital Y as a function of y, is e exponential of minus n pi over a y. That means that we can stick these two together and we're going to get that v is equal to, I have a and e, those are two different arbitrary constants that will be set. I can absorb them together, so I'm just going to call this a, then sine of n pi over a z times exponential of minus n pi over a y. You're good. So that's where we're sitting now, and we want to enforce at this point the final boundary condition for this problem. The final boundary condition is that at y equals 0 we have that v is equal to v naught. And so if we plug that in, we look at v r at y equals 0, we're going to find that exponential at 0 is just 1. This is a sine of n pi over a z. We want that to be equal to v naught. But that's never going to be the case, right? That for any function sine, no matter what I choose, is never going to equal a constant. So here's where we have to use a trick. We have solutions for any integer n, and we have the superposition principle. So truly for v, we should be able to write down something like this. v of r should be a sum over the n of a n sine n pi over a z exponential of minus n pi over a y. And now we're able to write down the problem a little more fully. And so we're going to get that the boundary condition we're going to look at now, v at r y equals 0, is equal n a n sine of n pi over a times z should be equal to some constant. And now we have a slightly different question, which is, can we find a sequence an that when summed up with signs will give us a constant over the range that we're looking at? This question of can we find a series of sine functions that give some other function is actually a very common question in many scientific fields and many just numerical fields, quantitative fields. This is known as a Fourier series. Okay, and so the question is, can we find the sequence an such that when summed up with the sine functions will give us some other known function, in this case a constant. Okay, and this uses the technique of Fourier analysis. Okay, so we're going to move on and we're going to work with Fourier analysis. Sorry, I should have been more prepared with my paper. So to start out, what we want to do is talk about one of the properties of these sine functions. We like the sine property called orthogonality. And that's this statement. Okay, if I have the integral from 0 to a d, let's see, z in our case, sine of n pi over a z sine of m pi over a z, this can equal two different things. If n is not equal to m, then I have a product of sines. And it turns out that when I have a product of sines with two different frequencies like that, I can write this as a sum of sines and cosines that's going to be a multiple of each frequency. Now, because I'm integrating over one period of this sine of n pi over a guy, then I'm always going to have as much up as I have down. I'm always going to integrate over a full period, so I'm always going to get 0. And so with this idea that this product here, when I have this, I'm always going to integrate 0 if m does not equal to n. So this is 0 if m does not equal to n. Now if m equals n, in that case, that's the same as sine squared of n pi over a z. Well, sine is not 0 everywhere, right? If I choose some z such that the sine evaluates to 1, for example, then that's not 0 everywhere. When I integrate a function that's not 0 over part of it and it's squared, I have to get a positive number out of there. So this is definitely going to give me some non-zero positive number. Now, sine squared plus cosine squared is 1. If I integrate 1 over 0 to a, I'm just going to get a. And I can kind of tell that if I shifted the limits of integration, I could change my sine to a cosine, my cosine to a sine, and it wouldn't change the integral. So it turns out each one of those is going to have to contribute exactly half. So the other option is a over 2 for m equal to n. So this is a property called orthogonality. So what we're going to do is we're going to use this to find these a of n's. So in order to do that, I need to multiply both sides by sine of n pi a over z. And so this is going to give me a sum over n, a n, and then I'm going to leave some space here, sine of n pi over a times z, and here's what I'm adding, sine of m pi over a times z. Okay. This is going to be equal to this v naught, and I'm going to add this sine of m pi over a times z. Now the other trick for the orthogonality is I need to integrate. Okay, so I'm going to integrate both sides from 0 to a. Now you see why I left that space. Now on the left-hand side, we've already decided we know what that is. This is this orthogonality property of sine functions. So over this sum is just going to give me 0 plus dot 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 until I get to the mth term, and then it's going to give me plus am, a over 2, plus 0 dot dot dot. Okay, so it's going to sum to am a over 2. On this side, the integral of sine is just cosine, so this is v naught a over m pi, and then it's cosine evaluated, it's actually minus cosine evaluated at 0 and a. The minus sign I'm going to absorb and switch my limits, and so this is going to be 1 minus, because that's the cosine of 0 is 1 minus the cosine of m pi. Okay, and so this is what we have on this side. So now just equating these two and solving for am, we get that am is going to be equal, the little a's cancel, 2 v naught, oh, and let's look at this for a while. For m equals 1, this is cosine minus minus 1, so this is going to give me a 2. For m equals 2, this is cosine minus cosine of 2 pi, which is just 1, so 1 minus 1, this is going to give me 0. For m equals 3, this is cosine of 3 pi, which is minus 1 again, which is going to give me 2. M equals 4, this is going to give me 0, and I kind of see a pattern here, so I'm actually going to get this 2 in here as well. So it'll be 4, here, let's start over, 4 v naught divided by, let's see, just m pi, I guess, m pi. And so that's the expression that we're going to look at. So now we can stick that back into our original function, which we have right here, and that is going to give us that v of r is equal, I guess our original function is here, is the sum over n, and we now know what these a_n's are, sum over n of 4 v naught over n pi sine of n pi over a times z times the exponential of minus n pi over a times y. And that's it. That is the potential everywhere in this infinite slot.